Hi, everybody. I'm William, and today I'm talking to you about pseudorandomness. Right, so a pseudorandom generator is a function that stretches a short, truly random seed out to a long pseudorandom string. And the way we make this pseudorandomness condition precise is that we consider some class of functions, this script f, and we require that basically that the output of this generator looks random to every function in that class. Okay, so the acceptance probability of a function in that class should be approximately the same, whether we're plugging in truly random bits or pseudorandom bits. And maybe the most traditional setting would be if we take this class script f to be like everything that can be computed in polynomial time or something like that. But for today, actually, we're more interested in the case that this class script f is like very restricted. And the benefit of looking at a very restricted class of functions is that then we can actually prove something. We can design pseudorandom generators that provably work. So like maybe the simplest possible example, here's a pseudorandom generator that stretches 2 bits out to 3 bits. Right? The class of functions that we're going to fool are just depth 2 decision trees on these 3 bits. So it's just a little toy model. And the generator says you take these the 2 bits of the seed x and y, and then you output x, and then y, and then the XOR of x and y. Right? This is like the classic example of a distribution that's pairwise independent, which means in particular that it will fool these depth 2 decision trees, things that only look at 2 bits. So that's just like a very simple, toy examples, trying to illustrate this concept, and that it doesn't necessarily have to be, like a conditional thing where we make complexity theoretic assumptions or anything like that. We can make concrete constructions of pseudorandom generators that work for simple sort of combinatorial reasons potentially. But of course, we're really more interested in classes F that are maybe a little more rich than something overly simplistic like this. And so, for example, just to give you some examples of my research on this topic with collaborators. So we've designed like explicit pseudorandom generators for restricted models of computation like read once bounded depth circuits or bounded depth threshold circuits or certain kinds of branching programs, things like this. And so when you restrict the model, then hopefully we get these models of computation that are hopefully still interesting. They're rich enough to do something interesting, but they're weak enough that we can actually fool them. So let me try to give you some motivation for why would be interested in theorems like the ones that I had on the previous slide. Why design pseudorandom generators for these models? Well, the most basic reason to design a pseudorandom generator is to try to decrease the number of random bits that you're using for some computational process. Okay, right? Because if you're using a pseudorandom generator, now the only random bits that we need are the seed of that generator. Okay, and so we want to think of random bits as being like a scarce computational resource, just like time or space. So just like a faster algorithm is better than a slower algorithm, we want to think of an algorithm that uses fewer random bits as being better than an algorithm that uses more random bits. And best of all is an algorithm that doesn't use any randomness, right? A deterministic algorithm. And that's also sometimes, depending on the context, that might be something that you can achieve with a pseudorandom generator, because to try to, to get rid of this last little bit of randomness, the seed of the generator, we can depending on the context, we can potentially just try all seeds and see what happens, for every single one of those seeds. Another reason to design pseudorandom generators is that actually sometimes they're useful for designing randomized algorithms. Just in some contexts, this comes up, like streaming algorithms is maybe a classic example. So that seems a little bit like the opposite of the previous goals, but and maybe actually the most important reason is a little bit subtler, which is just that when we design a pseudorandom generator for some class of functions f, if we're able to design an unconditional generator, a construction that we can truly just write down and analyze, then that really sheds a lot of light on this class f. It teaches us something about this model of computation. So you can think of a pseudorandom generator as like a highly refined type of lower bound for this model. It's giving like an example of a task that this model of computation cannot solve at all. It doesn't understand it at all, right? Because the pseudorandom generator is sampling some distribution that's actually, a very low entropy distribution, but it looks totally random to this class F. So it's like the class F has, no understanding of the structure that is actually present. So just to give you some idea of like what sort of problems there are to work on in this area, really one of the biggest open problems is to try to design better pseudorandom generators for space-bounded computation. This problem drives and motivates like a lot of the research in this area. Maybe some potentially easier problems, hopefully easier problems, would be like even for simple models of computation like read once CNS. Okay, so this is an AND of ORs of variables, and each variable only happens one time. Okay, or literals, I should say. We allow NOT gates also. And even for that, like very simple model of computation, we still don't have optimal pseudorandom generators. We have very close to optimal, but we're not quite there yet. And then there are also, interesting, other, somewhere in the middle, there are interesting models of like bounded depth read once circuits of various types where we can hope to design very good pseudorandom generators. And right now we only have pretty good pseudorandom generators. Okay, so let me slightly move on to a very related topic, which is derandomization. It already came up one time, right? One of the reasons to design pseudorandom generators is to try to derandomize algorithms, which I think is also just a nice goal in its own right. So as a reminder, this class BP space S is the class of languages that can be decided by a randomized algorithm that uses O of S bits of space. Okay. And the conjecture, the popular conjecture, says that BP space S coincides with deterministic space S. Right? So this conjecture is saying that randomness is not actually necessary for space-efficient computation. So you might as well take all your fair coins and throw them in the trash can. And so if you've ever studied complexity theory at all, you know that there are a lot of conjectures like this. We have all sorts of ideas about what we think is true about the relationships between different fundamental computational resources, like in this case, space and randomness. And in most cases, these problems are really extremely difficult, and people have been working on them for a long time with very little success. One thing that sets this problem apart a little bit is that I would argue that there's more hope of actually proving this compared to some of the other similar, superficially similar conjectures in complexity theory. And one piece of evidence for that, one reason to maybe have some hope about this problem is that we do have quite a few partial results. So I'll just mention a couple partial results that that are my own research, but there are plenty of other examples that I have nothing to do with. So one would be, we can at least say, all right, if we have BP space S, we can de-randomize that with, all right, there's some blow up in space, but we can bound the extent to which the space complexity blows up. And yeah, so currently the best bound is S to the 3/2 over square root log S, which is just this, this tiny improvement over, an older result from the 90s that got this S to the 3/2 bound. Or just, one more example would be if we restrict the class a little more, so we're not looking at just bounding space, but let's bound time and space. So let's look at problems that can be decided by randomized algorithms that simultaneously use quasi-linear time and logarithmic space. Okay. Then it turns out it's possible to de-randomize those in log space. The deterministic algorithm is no longer fast, but and then there's this extra caveat, which is that it's only like a typically correct algorithm. It gives the wrong answer sometimes. But. Okay, so just to wrap up, I just want to say, I don't think we have really any excuse for having not yet, proven unconditionally that BP space S equals deterministic space S. So I'd love to work on this problem with any of you. And let me mention just quickly, a couple of problems that are potentially easier on the way that I think are fascinating would be like proving that BPL is contained in NL, or maybe proving that RL is closed under complement. But anyway, thanks for listening, and I'd be happy to answer a question.